Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. If I told you a car's velocity was positive, you know that it was moving forward. And if it was negative, then it's moving backward. Calculus applies the same logic to graphs. By looking at the first derivative, we can peek under the hood of any function to see exactly where it's climbing, where it's falling, and exactly where it peaks. This is known as the increasing-decreasing test. Now, before we get into it, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. The increasing-decreasing test says that if the derivative of f is greater than 0 on an interval, then f is increasing on that interval. And if f prime of x is less than 0 on an interval, then f is decreasing on that interval. And this makes sense intuitively because if the derivative is positive, then that means we have a positive slope, which means the graph is going upwards. And if the derivative is negative, then that means we have a negative slope, so therefore the graph is going downwards. So let's take a look at how we can use that information. For our first example, we want to find the intervals of increase and decrease for f of x. To do that, we are going to find f prime of x first. And f prime of x here is equal to 4x cubed minus 12x squared. Next, we're going to set f prime of x equal to 0. So we get 0 is equal to, and then here we're going to factor. So this is 4x squared times x minus 3. And then we use this to find our critical points, which we get x is equal to 0 or x is equal to 3. So now recall, the reason we want to find these critical points is because the only way for f prime of x to change signs is potentially at those critical points. So once we've found those critical values, all we need to do is do a test point in each interval. So we're going to go ahead and draw our number line, and then we're going to label our critical values there. So we have two. One is at x is equal to 0, and one is at x is equal to 3. So we can see that we've divided this number line up into 3 different intervals. And now we just need to find a test point within each interval. And any number within that interval will work. So for our first interval, we can test what is f prime of negative 1. And this is going to be equal to 4 times negative 1 minus 3, which is negative 16. So therefore, it is negative over here. And then for our second interval, we can go ahead and test f prime of 1, and that's going to be 4 times 1 minus 3, which is negative 8. So here, this is also negative. And then for our last interval, let's go ahead and test f prime of 4. So this is going to be 4 times 16 times 4 minus 3, which is equal to 64. So therefore, we have positive slope there. So therefore, our answer is going to be on the interval from negative infinity to 0, our function is decreasing. And then from 0 to 3, our function is still decreasing. And then finally, the last interval, which is from 3 to positive infinity, our function is increasing. Next, let's take a look at our first derivative test. And the first derivative test says that suppose that c is a critical number of a continuous function f. Then, if f prime goes from positive slope to negative slope at c, then f has a local maximum at c. And that makes sense because that means you were going up, and then after c, you're going down. So therefore, this is a maximum. And similarly, if f prime changes from negative to positive at c, then f has a local minimum, because that means we were going down originally, and then after c, we start to go up, so therefore this here is a minimum. And then lastly, if f prime does not change signs at c, then f doesn't have a local max or a local min. So now, armed with this new information, we're asked to find the local extrema of the function from example 1. So from example 1, we had 2 critical points. So critical points, we had x is equal to 0 and x is equal to 3. However, at x is equal to 0, our derivative did not change signs because it was decreasing from negative infinity to 0 and then still decreasing from 0 to 3. So therefore, x is equal to 0 is not a local extremum. Now, at x is equal to 3, f prime went from negative to positive. So therefore, we have a local min at x is equal to 3. So therefore, to find the value of this local extremum, we just need to substitute our x value into our original function. So we get f of 3 is equal to 3 to the power of 4 minus 4 times 3 to the power of 3. And this is equal to negative 27. So here we would say a local minimum happens at x is equal to 3 with a value of negative 27. And let's just go ahead and take a quick look at what the function looks like. So here we have our f of x is equal to x to the power of 4 minus 4x to the power of 3. So if we zoom out, you can see that we have our two critical values, one at x is equal to 0 and one at x is equal to 3. Now what happens at x is equal to 0 is that even though we have a horizontal tangent line, the graph doesn't change direction. It continues going down. And then at x is equal to 3, that is where we have our local minimum because the graph went from going downwards to going upwards. And now let's do a quick recap of what we covered in this video. We went over the increasing-decreasing test, which says that if the derivative is positive, then the function is increasing. And if the derivative is negative, then it's decreasing. And we linked it back to critical points, which were introduced a couple videos ago. When we introduced critical points, we said that's when the derivative is 0 or undefined. And we said that those are potential candidates for when the graph could change direction. And now, combining it with the increasing and decreasing test, we have our first derivative test, which says that if the derivative of f changes from positive to negative at a critical point, then we have a local max. And if the derivative changes from negative to positive at a critical point, then we have a local minimum. And now it is your turn to give this a try. Can you find the solution to the problem on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.